Welcome, everyone. Today, we will get started by applying what we know about testing hypotheses to a new situation, which is a very common situation that you encounter as a data scientist. But as always, announcements. Same announcements as before, date and time of the midterm. Tonight is the very, very last time you have to tell us that you need the alternate time. There are now 2 midterm prep posts. One of them has past exams with suggestions for which ones to focus on. And the other one has logistics and so on and so forth. They're pinned on Ed. So what we'd like to do, remote midterm, yes. So what we would like to do today is to review where we were last time, talk about some generalities, and then Professor Wagner is going to pick up and apply those general methods in a new situation. And so what I would encourage you to do as you go through the next few lectures is to, of course, you'll be focused on the particular, but also try to step back and see, okay, so what was the general approach that was being used here? Because there is a common general approach. Okay, so on Monday, we assessed the consistency of data and a couple of models about the randomness of the selection of a jury. On Wednesday, we talked about, we discussed the terminology and the general method, and we were sort of in the middle, towards the end of that discussion where when we left off. So I'll pick up there. We'll talk about a little bit of terminology and the way to make conclusions and the logic behind that, and we'll discuss, how often can you be wrong, and then we'll pick up with applying everything that we know in a slightly new situation. So we had started out with the issue for us was we had 2 views of how the world was. In other words, 2 views of how the data were generated. These are called our hypotheses. Yeah, these are conjectures that we are making, and then we have some data. And our goal was to choose between one of these 2 views, the criterion being consistency with the data. That's the best we can do under the circumstances. So the views are called hypotheses, and they have, in the context in which we are working, the 2 have slightly different status. One of them, which is called a null, is a model under which you can simulate data. So well-defined chance model means it is completely specified how you are simulating the data, right? How you intend to simulate the data, that you're going to draw at random with replacement from such and such distribution. So, and that is what will allow you to do the simulation, right? If you leave the specification incomplete, then you can't simulate. The other one, brilliantly, is called the alternative. And it is a different view of the world. And this may be a chance model, it may not. It's an opposing point of view, and typically, almost invariably actually, it is such that you can't simulate data under it, right? It has a different status in that sense. And so what do we do then? We decide on something to measure that will help us decide between these 2 hypotheses. That is called a test statistic. It is a quantity that we will calculate based on our data that will help us decide between our 2 views of the world. And so when you choose the statistic, you have to first ask yourself, okay, so on this number that I'm going to calculate, how am I going to use it? What kinds of values will make me lean towards the null hypothesis, and what kind of values will make me lean toward the alternative? right? And very often it is, small values are going to make me lean towards one, big values are going to make me lean towards the other. Or if the values are all kind of around 50, I'm going to think null. But if they're sort of all bigger than 70, then I'm going to think alternative. That kind of decision you make. And you choose your test statistic based on that. And this is a very key element, because this is the statistic that you are going to simulate under the null hypothesis, this quantity. So you're going to draw a sample, you're going to compute this quantity, note it down. Then you're going to draw another sample, you're going to compute this quantity for that sample, note it down. And you're going to do this thousands and thousands of times. And that will give you, let's ignore that for now. That will give you a prediction under the null hypothesis. Okay, so you simulate, pretend that the world is what the null hypothesis says it is, and then see how the data should come out. So you predict under the null hypothesis. And what you get is an observed distribution of the statistic under the null hypothesis. And so that is your prediction. And on the horizontal axis, it shows you what that statistic is likely to be if the null were true. And the areas show you the chances of what all of those different values, if the null were true. Okay, so that is essentially a mind game. It's a prediction made by a mind game. And now you actually have to make a decision. So what do? You've made your prediction, and now you have to see how it stacks up. So you have to compare. You have to compare what you actually got as the statistic, which is the observed statistic, which is from your sample, that's your data, and you compare it with the prediction, and then you decide whether it's consistent or not. So we had stopped at how do you decide whether it's consistent? And so what I'm going to do is I'm going to move over to a notebook and kind of go and quickly review the model that we were looking at. So this was Mendel's model for the color of flowers in pea plants. And what he had postulated was that each plant had 75% chance of being purple flowering, independent, regardless of all the other plants. And we were testing, is that model good or not? Right, so we had to decide first, what is the statistic that we are going to use? And so what's he predicting? He's predicting 75% purple. So a natural thing to look is to see how many what percent purple we got in our sample and compare with 75. Now, this comparison, if the difference between these two numbers, what we observed and what Mendel is predicting, 75, was small, then we're going to say, oh, the data look consistent with the model. But if the distance is large, which means if the proportion in the sample is either much smaller or much larger than 75, then we are going to worry. Then we're going to say maybe something wrong with the model. So that is why we chose to use the distance, that is absolute value. Can you actually, hold on, I'm going to do something. I'm going to stop sharing. Can you see my hands? Absolute value? Distance. This is the symbol that we use with our hands all the time when we're talking about distance, right? And did you notice this is the symbol for absolute value? All right, so distance. So that is why we chose the test statistic, and we were very careful. Small values of the distance will make us lean towards the null hypothesis, and large values will make us lean towards the alternative. And then we had a simulation. We simulated one distance based on the null hypothesis. Then we did a bunch of them. And then we had a prediction. And the prediction looked like this. On the horizontal axis are all possible distances, assuming that the null hypothesis is true. And these are all the probabilities. I should say, to be really a stickler, these are approximate probabilities because we're only doing 10,000 repetitions. If we had done 50,000 repetitions, we'd have got something slightly different, but that's still good enough. And so now we compare with our actual observed distance, which happened to be right here. And in this particular instance, I think there's very little doubt that what we observed is quite consistent with what the null hypothesis is predicting. Okay, and that's great. So we have a decision that we can say, okay, these data are consistent with the null hypothesis. I don't have a reason at the moment to doubt Mendel. However, actually, in earlier situations, we've had observed values coming out here when the null hypothesis prediction was sort of here, and then it was very, very clear that the observed data are not consistent with the prediction. But the question always arises, yeah, well, what if my observation was here? Then what would I do? Because then it is not so clear, right? And then that is where we were when we left off last time. And before we go on, I'd like to take a few questions about what's in this diagram here. Is everybody clear about what it represents? We're going to look at more diagrams like that, and I'll talk in greater detail about all of the different pieces. So I'm waiting for somebody. Somebody said no. Could you ask your question? Okay, maybe I will leave it to my colleagues who are watching the chat to take that question, and I will go back to our slides. And so this is how we're going to decide consistent, but consistent is a subjective judgment. And that is the thing to take away. It is a subjective judgment, and we are going to be making a subjective judgment. And I know that's a little unsettling, but really, in the end, you have to make a decision based on uncertainty. And there isn't a sort of universal law of how uncertain or what's too unlikely. Okay, so let's talk about meanings of not consistent. So this is based on the way we decide about consistent is we say, okay, look, here, this is kind of in the heart of the area right here. It's the heart. And so this, I think, is consistent. But if it was out here, I would start wondering. And so what we notice is that that decision does not depend on what numbers are along here or what numbers are up there. It depends on the shape of this curve and where you are relative to that shape. And we also notice that the place we start worrying is in the tails. Okay, and so that is one way of intuitively understanding why the decisions are made the way they are. The decisions are based on the tail area. If a tail area is small, then you are far out into the tail. In our case, the rule being you start at the observed value of the test statistic, and then you think about the alternative, okay? Because what's my other hypothesis that I'm going for? That's the alternative hypothesis. And you look in the direction that favors the alternative. This we'll talk about quite a bit. And if the tail is small, then you're kind of thinking alternative. And if the tail is not small, then you are thinking, maybe null is okay. And all of this sounds like talk. Let's just do it in a particular case. When testing Mendel's model, the alternative is the model is not good. The statistic is a distance between the data and what was predicted by the model. So large values of the statistic favor the alternative. So we will look at the point that we got or to the right towards larger values. And so we will look at that tail area. Now, do you agree that that is a substantial tail area without doing any calculation? Right, so what this is saying, this entire histogram is a prediction by Mendel's model. And what we are saying is that if Mendel's model were true, then we have a massive chance of seeing data like the data we saw, or even worse, that is even further away from the model. So, that these kinds of data are pretty likely based on the Mendel's model. And so it's reasonable to conclude that this is consistent. So shall we actually find what proportion this is? How about that? Should we do that? we have all the data, so we should be able to find that proportion. This is the picture that we're looking at, and we want to find the shaded area as a proportion. And now the array was called distances. All of the distances are in this array distances. And so what do we have to do? We have to count the number of the distances that were greater than or equal to this observed distance, and then convert that to a proportion. The tail area is yellow. I'll be talking a little bit more about that in just a moment. So we're computing the proportion to the right. Okay, and so we do np.count non-zero, which the distances that were bigger than the observed distance. And we look at that as a proportion of the number of simulations, and we have almost 55%. Right, so what we're saying is that if Mendel's model is good, then we have almost a 55% chance of getting a distance like the distance that Mendel observed, or even bigger. So that's a substantial chance. So the null hypothesis prediction and the data seem consistent. So what we'll do is go now and look at another situation, and without doing any of the calculations, we'll see how we can make the decision. So I have a coin. I have some reason for thinking it's biased towards tails. If a coin is biased towards tails, then I typically have fewer heads, right? For some reason, I'm worried about this coin. So I'm going to test fair versus biased towards tail. Now, my null hypothesis is the coin is fair. Why? Because I can simulate a fair coin, right? The array is 0.5, 0.5. My alternative hypothesis is the coin is biased towards tails. I want you to notice that you cannot simulate under this hypothesis because you don't know how biased. Okay, you're not even specifying how biased. Okay, the statistic I plan to use is just the number of heads. Now, small values of the number of heads are going to favor the alternative hypothesis. And so what we're going to do when we look at our prediction under the null is we're going to look at the value of the number of heads that we got or fewer. Let's just look at that data. Okay, so now what I would love to do is to remind you that there are three main aspects of this decision. There's the null hypothesis, there's the alternative hypothesis, and then there is the alternative. And let's look at these three colors and notice how each of the three colors represents a different piece, a different one of those three. The blue histogram, which actually includes this yellow tail as well, that blue thing is a prediction under the entire histogram, is a prediction by the null hypothesis. The red point is the observed data. The question is, what's the yellow? Okay, well, you have the null, you have the data. What is the other view of the world? That's the alternative. So the question you ask yourself is, if the null were true, what is the chance that I would be misled into thinking that it was like the alternative? And there you remind yourself that small values of your statistic make you look like the alternative. And so the fact that you are looking left came from the alternative. The tail is determined by you start at the observed value and you look in the direction that favors the alternative. In this case, small values favor the alternative. And so therefore, you're going left. Okay, so now this question is that too far out in the tail or not? Well, obviously you can make your own decision, okay? But there are some conventions. And why does my slide never work? Okay. The conventions are, in order to decide what is inconsistent with the null, is how far out in the tail is too far. So if the tail area is less than 5%, that is conventionally called small, and the result is called statistically significant. And if the tail area happens to be even smaller, less than 1%, then the result is called highly statistically significant. And that's all very well, but these terms have done a lot of damage because people spout them without actually thinking through about what they mean. And so what I would love for you to do is to notice that these statements like highly statistically significant, which makes it sound like something very, very important has happened, is actually just a term for how a chance came out. Highly statistically significant means somebody somewhere computed a chance, assuming a hypothesis that involved randomness, and that chance came out to be less than 1%. Now, the degree of importance that you give to it is really up to you as the domain scientist. Okay, but it's important to know this terminology because you see it everywhere. You're going to see it. In fact, if you read journal articles, they will not give you the entire analysis that they give you this last thing. The value of the statistic, that tail area that they found, and then they'll put a star if it's statistically significant or a double star if it's highly statistically significant. So you have to understand what is being done there. And so hence you have the terminology. Okay, so that gold area is called the p-value. It has a more jaw-breaking formal name, but we won't go into that. It's in the textbook if you want. So because you will be computing that tail area, you have to be able to refer to it. It's called the p-value. So what is it? It is a chance. Okay. It is under what assumption is it computed? Somebody. Under which hypothesis do you compute? Under the null hypothesis. Thank you. Of getting an observed a test statistic that is the same as what you observed, or even more in the direction of the alternative, this way. And how do I know to go left? Because the alternative says small numbers of heads in this particular instance, right? In whatever other test you're doing, you will have to decide what is the right direction for the alternative. So it's if this chance is compared to 5% or 1% to see if it is small. And that is how conventionally the decisions are made. So let me just pause for a second to take a few questions. A p-value is, okay, so let me be precise. The proportion that we computed from these empirical, from these simulations was approximately the p-value. It is the proportion, this area is a proportion of the 100% total. There is an actual p-value that would have appeared if we had simulated every possible sample. That would have been awfully close to what we got. So really, if you want to be a stickler, this is an approximate p-value that we're getting. The test statistic is this point. The p-value is this gold area. Okay, so now this raises a question. We have decided that if this tail is very small, then we are going to reject. But couldn't the fair coin give us a small number of heads just by chance? It could, right? It's not hugely likely, but it could. And so in that situation, you could have a fair coin that gives you data that really looks like the coin is unfair. And then you will say, you know what, I don't like it. I don't think this coin is fair. I think it's biased towards tails. And you will be wrong. So we have to assess the possibility that we could be wrong. And now here you have 4 ways the world can be. There you go. Either the null is true or the alternative is true. Those are 2 ways the world can be. And your test is either going to conclude consistent with the null or reject the null it's pointing towards the alternative. In 2 of these situations, your test is giving you a good answer, right? Given that the null is true, if you conclude consistent with the null, your doing well. If the null isn't true and you conclude alternative, then also you're doing well, but you have two ways of being wrong. There are two distinct ways. And what the method of making conclusion does, it gives us a handle on how frequently we make this error. If the null is true, then what is the chance that you're actually going to be wrong? And so what I'd like to do is I would like to go back to our data here. And let me ask you, if you're under Mendel's model, if the point had been here, what would you have decided? So just say, supposing it was 4, the distance, what would you decide? Good or not good? Right here. You would reject the null hypothesis, you would say not good, right? Okay. Here we said null, here we would have said null. What about just about here? Well, we're not sure. Okay, so there is a point where there is a different decision that is being made. And so what is that point? Well, that has to do with what you have decided to call small, right? If you have decided that 5% is your cutoff for what is small, then there is a very important point here, which is if you go along here, here, where is 5% as the area? That is a very important point because that is where your decision changes. And so what we're going to, well, around 3, is that 5%? I don't know. Let's see. Let's look at 3. 3 looks kind of right. Okay, so the proportion beyond 3 is actually only about 3%. So I tried, just trial and error, I tried 2.85, and I got the area to the right of that is 4 and a bit percent, 2.8. Sorry, 2.9. So I'm looking for 5%. Kind of 5%. I'm not going to hit it exactly. Okay. So let's just say 2.75 is our point where we have where there's the 5% break. Okay. That area is 5%. So everything, if my statistic came out to be 2.75 or more, I'd be concluding alternative. If it came out to be less, I'd be concluding null. But if the null is true, this is the prediction. If the null is true, can your statistic be 3? Question to you. It can. It's right here. Can your statistic be 2.8? Yes, it can. Can it be 3.5? Yes, it can. For all of those values, you will conclude that the model isn't good, and you will be wrong. So take a look at this picture. What is the chance that you will be wrong? It is the chance that you get a statistic in this range here. What is that chance? 5%, roughly 5%. That's how we found it. That cutoff is your error probability. Okay, it's the probability of this error. If the null is true, what is the chance that you make the wrong conclusion? That is what the cutoff is measuring. So the cutoff for the p-value is an error probability. If the null is true and your cutoff is 5%, then you have a 5% chance of concluding wrongly the alternative. And so I think we just did the demo I was intending to do. And so here is a graphical summary of what we just said. You have a prediction made by the null hypothesis. You have this point here that is called a critical value. This is the 5% point from the right-hand side. If you want, you can call it the 95% point from the left-hand side. Why are we looking at this point? Because we have decided to choose 5% as our cutoff. Okay. In that case, all of these values, statistics of all of these values, will lead us to conclude the alternative. And all of the lesser values, we will say that the conclusion is that the data are consistent with the null. If the null is actually true, we have a 5% chance of getting values in this range, and therefore a 5% chance of being wrong. Okay, so that cutoff has an interpretation as an error probability. Now this number 5%, where did it come from? It's not any universal constant. I want you to know, we've been saying, you know, what is small is subjective. I really want you to know where it came from. So Sir Ronald Fisher is the statistician who came up with this way of making decisions, and it has just become enshrined in science and social science everywhere. Look at what he's saying. We have the duty of formulating, of summarizing, communicating our conclusions in intelligible form, in recognition of the right of other free minds to ultimately make their own decisions. Tell me, does that seem to you like a person who is really didactic, who will say, no, you have to use the threshold, that this particular threshold and no other, you cannot think for yourself? Does that sound like such a person? Quite the opposite, right? He is giving us the respect of saying, you know, you guys are smart, you make your own decisions. So where did the 5% come from then? It came from a paper that he wrote, where he said it is convenient to take 5% as a cutoff. Convenient to whom? Convenient to him. Indeed, the next year he wrote, you know, if 1 in 20, that's 5%, right? If that doesn't seem, you know, right to you, then you might draw you might use a smaller cutoff, right? You might use 1 in 50, you might use 1%. Now look, personally, the author prefers to set 5%. Okay, does that sound like the man saying, all of you guys, 5% is the definition of small from here on out? It does not. He's just saying that he likes it. Now, what happened in the world, you know, when we give you problems to do, and there's a lot of words and some numbers in between, you guys, there's a lot of people who read blah, 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 number, blah, blah, code, blah, blah, number. That's exactly how this paper was read. People ignored all the words and saw 5%, and that's it. And it's used now and forever. But it was Fisher's personal preference. So our recommendation to you is please, please, please do say what your statistic was, say what you are using as the cutoff, and let the readers make up their own minds. Okay, I'm going to stop now and turn over to Professor David. And I will be on ED all day to answer all of these questions that you are raising.
Howdy, howdy. Oh my gosh, I am loving so much engagement and interaction today. All right, so I'm going to talk about another kind of hypothesis test called A/B testing. And A/B testing is also a hypothesis test, and it's used in a particular situation. So far we've been talking about hypothesis tests where we draw one sample and we have some model for how we think maybe the data were produced, how we think maybe the world works. Now I'm going to switch gears a little bit. Sometimes we don't have one sample, we have two samples of data. We have two samples that were drawn somehow. In other words, two groups of observations, and we want to test whether they came from the same distribution. In other words, we want to test whether they were generated using the same process. So let me give you an example you could think about. Like, let's say we do a medical trial. And it's really common that we have a treatment group and a control group, right? Maybe we do a randomized controlled experiment. We talked about those before. And so some of the people are in the control group, they didn't get this experimental medication. Some people in the treatment group, they did get the experimental medication. All right, so now we've got two samples. We've got the measurements from the control group. You can't see me. Well, now, okay. Let's make an adjustment and see if I can fix this up. I think we can make this work. I'm so sorry here. Let me, I am fighting with Zoom. Or it's pinned or spotlighted on Zoom. All right. Now let's try again. Maybe this is going to work this time. So sorry for the delay. How is this now? Yay. Okay. My fault. I messed up my Zoom settings. All right. So you got this medical experiment with a treatment group and a control group. You got measurements for the patients in the treatment group. You got measurements for the patients in the control group. Those are two samples, a sample of data for the treatment, sample for the control group. We'd like to know, did this medication do anything or not? Okay. If it did nothing, then effectively both of those data were generated in the same way with the same biological process. In other words, from the same distribution. So we'd like to test whether or not that's the case. All right. So whenever you have two samples of data, then this technique I'm about to show you, A/B testing, is a useful way to do a hypothesis test. And one thing that's nice about this case is I don't have to be able to write down a chance model that describes how the data were generated. All I need to be able to do to assume in my null hypothesis is that they were generated in the same way, whatever way that is. Okay, so the A/B test is going to help us compare the values we get for group A to the values we get for group B to see if there appears to be any difference that is meaningful or whether any small differences we see might have just been caused by chance. All right, so the question is, do this two sets of values come from the same underlying distribution? In other words, was the same real world process generating both sets of data? So let's take an example. I'm gonna work with a data set that was collected by researchers who were studying the effect of smoking. When a pregnant mom is smoking, the effect of that on the baby. And in the field of medicine, of people who study newborn babies, it turns out there's a very effective way to measure the health of a newborn baby. The weight of a newborn baby is interestingly, a good measure of the health of the baby. And on average, underweight babies, that tends to indicate some kind of a health issue. So researchers went to this hospital. I have in my mind, it might've been a Kaiser hospital in the Bay Area, but I'm not sure if that's right or not. They collected for a bunch of mothers who just gave birth, the weights of their babies, and they asked the mothers, hey, do you smoke or not? Okay, so here's the data set. You can see in this data set, we have one row per baby, and there's a whole bunch of data here, but the relevant ones to look at is the birth weight here. That's the weight of the baby at birth. And then maternal smoker indicates whether or not the mother was a smoker or not. Okay, so we're going to only focus on the relationship between those two attributes, whether the mother is a smoker or not, and the weight of the baby. In other words, that's a kind of a proxy for the health of the baby. And So one of the questions the researchers wanted to know is there an association between those two? Is there a relationship? Here we have in this data set, we have 459 smokers and 715 non-smokers. And we can do a histogram of the weights of the babies for each of those two groups. And you can see here in yellow are the babies of smokers, and in blue are the babies of the non-smokers. Thank you, Professor Adhikari. Yes, this was a randomized experiment. The observed data here, the babies in this table, are a random sample of all the mothers who gave birth in this hospital system. Okay, so it's randomized, but it's not a controlled experiment, right? So mothers were not assigned to smoke for 9 months or not avoid smoking for 9 months. So we have two samples. We have two random samples. We have the random sample of the smoker moms. And this is not all the moms who gave birth in the hospital system. It's a random sample. And the random sample of the non-smoker moms. Now, if you look at this histogram, what do you think? Do you think that there is a relationship between smoking, mother smoking, and the birth weight of the baby? Yeah, maybe. Hard to tell. Okay, probably could be. I'm happy with all those answers. Look at the shape of the yellow curve, and it's a little different from the shape of the blue curve. The yellow curve looks like it's a little bit more nudged to the left, nudged to lower baby weights. So it kind of superficially looks like maybe the weights of the smoker babies were a little bit lower, tended a little lower than the weights of the non-smoker babies. But it's hard to tell whether that's a real difference. They're pretty similar. So it could just be that there was some random sampling here, and maybe there's just some random chance that we just happened to choose among the non-smokers some moms who had a little bit heavier babies. And really, maybe there's no real pattern in the population, in the real world, and maybe just as, you know, in the sample. In any sample you draw, there's a little bit of randomness. So you would expect there's going to be some difference. And the question is kind of, is this difference big enough that it looks like it represents something about reality, about the effect of smoking, or is it so small that it could be accounted for by just chance variation in the sample? Okay, a little tricky to tell. So let's develop a technique that the A/B testing is going to help us answer that question. All right, so let's look at what we've got here. We've got a random sample, and we're going to compare the birth weights of the babies of smokers and the birth weights of the babies of non-smokers. And there is a difference here, a small one. And so we're going to ask, could this difference be explained by just random chance in the sampling procedure? If it can't be explained by random chance, then that suggests that there's something in the world that is causing a real difference. Okay. In this case, because the weights of the smoker babies was lower, if that's real, that would indicate health problems with the smoker babies. In other words, it would indicate that smoking harms the health of the babies. So there's something real at stake here. But if the difference is just due to chance, then it indicates that smoking, there's no evidence from this data set that smoking is affecting the health of the babies. All right, so the hypotheses here, we need to write down a null hypothesis and an alternative hypothesis. The null hypothesis, roughly intuitively speaking, says, there's nothing interesting going on here, like smoking has no effect. So more formally, what the null hypothesis says is that both data come from the same distribution. In other words, the distributions of birth weights of smoker babies, if you could get the entire population from the entire hospital system, or from the true distribution of how biology works, the distribution of birth weights of smoker babies is the same as the distribution of birth weights of non-smoker babies. That's the null hypothesis. Okay. So the null hypothesis says, I know it looked like there's a difference in the sample, but that was just random luck or good or bad luck in who happened to show up in the sample and who did. The alternative hypothesis says, nah, null hypothesis is wrong. It's not the same distribution. In particular, the non-smoker babies are heavier and the smoker babies are lighter on average. In other words, the average weight of the smoker babies is lower. And if you could get the entire population, the average weight of the smoker babies in the population would be lower than the average weight of the non-smoker babies. Okay, so now in hypothesis testing, we need a null hypothesis, we need an alternative hypothesis, and we need a test statistic. In this case, we have two groups. So our test statistic is going to be a number that we're going to compute from the data, from the weights in group A and from the baby weights, the birth weights in group B. Can you suggest to me a way to summarize all the weights of all the smoker babies? If you had to summarize in one number, what might you use? The mean, the average? Sure. And if you had to summarize the weights of all the non-smoker babies, the average would be reasonable. So that gives me two numbers, two averages. But I really want to know, I want one number that captures whether the non-smoker baby seems to be lighter on average than the smoker babies. And so a way to get that is to look at the difference between those two averages. All right, so that's what we're going to use our test statistic. We're going to compute the average weight in each of these two groups, and then we're going to look at the difference. Okay, so we're going to look at the non-smoker average minus the smoker average. All right, if this difference is really large, that means that the non-smoker babies are heavier on average. So if it's really large, would that make you tend to think, I'm thinking the null hypothesis, or would that tend to make you think, no, I'm leaning towards the alternative hypothesis being correct? Alternative, yeah. That would make you think that that smoking is influencing things and causing the smoker babies to be lighter. All right, so large values of this test statistic favor the alternative. So we've now got a setup where we're ready to do hypothesis testing. We have a null hypothesis, we have an alternative hypothesis, we have a test statistic. We did a cross check, good. Larger values of the statistic favor the alternative, smaller values favor the null. So now what we need to do is we need to compare the observation, in other words, compare reality to the predictions made by our model, the predictions made by the null hypothesis. We have reality, we have the observed data. So now we want to figure out what the null hypothesis predicts. In other words, we want to figure out what distribution of the test statistic the null hypothesis predicts. And we're going to use simulation to do that. And on Monday, I will show you how to do that. And we will finish off this example and figure out whether indeed smoker babies had on average a lower birth weight than non-smoker babies or not. Have a great weekend, everyone. Thank you.
Professor David, can I say something before you turn off the recording?
Please do.
Which is that there are 3 numerical examples of A/B testing that we are going to do on Monday and Wednesday. We're going to complete this one, do another one, and a third one on Wednesday. So we'll have done a number of examples so that you can see all of this stuff in action, and we'll have plenty of time to answer your questions about testing hypotheses. So I know the midterm is coming, so I'd like you to know what is coming up in the lectures. That's all.